Welcome back to ECE 207. Have to remember where I'm at, what room I'm in. Today, your homework number 4 is finally due. Homework number 5, which is on AC circuit analysis, is due a week from today on the 19th. And we are having a runoff election to determine exactly when exam number 2 will be held. So please take that opportunity to turn in and accumulate some class participation points with your vote. If you cannot make one of those 2 dates, please indicate the reason and on your vote page if there is a reason why you cannot make the 21st or the 28th. Should I leave that up for just a little bit longer? Let's get started. Today what I want to do is talk about AC power in circuit elements, and that will lead us naturally, I hope, into this concept of complex power, which is a generalization of the power that we've been talking about. When we were talking about DC circuits, we had power in the resistor, which was I squared R. We've now generalized that R resistance to encompass Z's or impedances, and we now can associate impedance with not just resistors, but inductors and capacitors. And we need to use that in our analysis to make our life a little bit easier, meaning we don't have to worry so much about solving differential equations with sines and cosine excitations. We can jump into the frequency domain and analyze those with complex numbers, similarly to how we've analyzed DC circuits with just pure resistors. That's where I want to go today, is start the discussion with power in the individual circuit elements and then move into the concept of complex power. And complex power doesn't mean complicated necessarily. It just means that there's now going to be a real component of power that you pay your bill on, and there's also this concept, or actually quantity, of complex power that you probably don't get charged for, but industrial customers do. They actually have to pay for imaginary power, or volt amperes reactive. And we'll talk about that as we get there. Let's now look at AC power in these different circuit elements. And regardless of the vote, the material for exam number 2 will be based on homework 3, 4, and 5. Sorry, but my back was going to get sore. Kind of a whammy. All right, let's look at the resistor. Here's R, and if I sketched a current I of t, then you might want to label the voltage, consistent with our passive sign convention, to be plus to minus, meaning the current is going to go into the positive terminal of that resistor. But it really is not that critical which way we put the current or the voltage labels on this resistor. It's always going to be absorbing power. That power may oscillate. It may be less at certain times than at other times, but we will have power being absorbed by the resistor. Let's convince ourselves of that concept. Suppose that we have a voltage given by a magnitude V sub m, and it's a cosine waveform. Then we know that the current, because it's a resistor, we know this current voltage relationship, and they are actually in phase. with one another means there's no phase shift in the argument of either one of those cosines. They're at the same frequency. The omega is the same. And we know that Ohm's law is true. Where this R for this class, we are assuming that that is constant unless we have some sensor whose resistance is varying as a function of something. Maybe we have a bridge that's instrumented with a strain gauge and we now have resistance that's varying or adjustable, but we will just assume for now that that resistor is constant. What's our instantaneous power in that resistor? There's a lot of different formulas for the power, isn't there? Instantaneous power for a resistor. Maybe the easiest to remember is V times I. If we take that and we already have V times I functionally up above, then we have their magnitudes, V sub m and I sub m, and we have the cosine of omega t in both pieces, which says that then we have cosine squared of omega t. One thing that you can observe from that expression is that this piece, maybe I should say, is non-negative, but it's positive, and these amplitudes are also positive by definition. Consequently, we know the instantaneous power, no matter what time is always going to be non-negative in a resistor. Let's expand that or rewrite that, because it's not real easy to think of this sinusoidal waveform squared. Let's write that in terms of another sine or cosine of a particular frequency. And if you remember your trig, there's this relationship on cosine squared. Cosine squared is 1/2 plus 1/2 cosine. What's my argument? To omega t. Meaning now the power is a function of time. It's not constant, but now it's time varying, and the time varying piece is actually time varying at twice the frequency of the voltage or the current. The voltage and the current were both at the same frequency omega. The power is actually oscillating. It's a function of cosine with an amplitude of 1/2, and now we have a DC offset of 1/2. But the time varying piece is actually varying at twice the frequency of the voltage and the current. So that we could then say that we have a V sub m I sub m over 2 piece, and we have a V sub m I sub m over 2 times the cosine of 2 omega t piece. Here's our time varying piece, and we have this constant piece. If I ask you for the average power, this is the instantaneous power, that expression. This is P of t. That's for each instant of time t. If I said, okay, what's the average power absorbed by that resistor? Okay, so we could physically integrate that out and say, okay, here's P of t, let's find the average power. That would be the integral of this P of t over one period and divide by the period. But by just looking at this, what's going to happen when we integrate a cosine? And this cosine now has two periods within the fundamental period of the voltage or current. What happens if we integrate two periods of a cosine waveform? 0. We have positive area and we have negative area, and those will equal each other. And if we integrated or found the average power, that time-varying piece would average out or go away. It would average to 0. Consequently, the only thing we're going to see in the average power is that constant piece. If we integrate a constant from 0 to t, we get that constant times t, but we said we want the average, so we're dividing by the t. We're just going to get that constant back. The P average, or the average power, then, experienced by this resistor is just that piece. And do I have that figure? I think this is figure 521. Did I not label it? I guess not. The above two curves, the black curve is the voltage, the blue curve is the current. You multiply those point for point to get the instantaneous power, which is this second curve down below. And you can see that the instantaneous power is oscillating. And the number of cycles you see in the length of time that you see one cycle for voltage and current is actually two cycles. So it's twice the frequency. And you now see that, oh, it's always positive, it's always above the horizontal axis. The DC value is right there. It's an offset of V sub m, I sub m over 2 with this oscillation around that average value. And that's what we derived. Questions on that? That's the power, and that particular red dashed line represents this average power that would result if we integrated that instantaneous power over one period. A couple of observations. The power is always positive. That blue curve, that bottom blue curve, was above the 0 line and on the horizontal axis. Power is always positive for a purely resistive load. And this particular, or any resistor, the resistor always absorbs energy. Now, that particular power is fluctuating, but if you integrated that over time, all of that is going to give you basically the area under that curve, which would be the average value over the length of time that you're integrating to give your energy absorbed by that resistor. Questions on power in a resistor. That one is really no different than power in a DC circuit in terms of the expression or the equations. The resulting function is obviously different. In a sinusoidal in a resistor that's sinusoidally excited, its power will fluctuate, but its average power will be Vmax Imax over 2. Let's now look at some more interesting circuit elements, and in particular the inductor. With a value of L. The passive sign convention will be used. There's the current. There's the voltage. Instantaneous. And remember what we have. What did we derive last time for the impedance of that inductor? What is this complex quantity Z sub L? Is it a function of frequency? Is it more than just L? What's Z sub R for a resistor? That's just R, isn't it? The impedance for an inductor was omega L at 90 degrees. Or it was J omega L. Maybe you remember it that way. That's your complex impedance if you're dealing with inductors that are in a sinusoidally excited circuit. Now, if we have a voltage on that inductor, we can find that if we were given the current by this product, which is a generalization of Ohm's law now applied to sinusoidal circuits. So that I sub L is equal to V sub L over Z sub L, which we could say, okay, if this is I sub L that we're looking, and if we apply a voltage with magnitude V sub M that's a sinusoidal voltage at a phase of 0 degrees, then to convert that or find the current flowing through that inductor, we would divide by the inductor's impedance, which is omega L at 90 degrees, or we now have this V sub M over omega L at what angle? We now need to subtract the angles. The bottom is subtracted from the top, giving us this minus 90, and we might call that then I sub M at minus 90 degrees. Let's now write down the phasors associated with that above discussion or analysis. We could say, okay, we have a voltage phasor for the inductor with a magnitude V sub M and an angle of 0.
Why does the voltage not have a phase angle?
The question was, why does the voltage not have a phase angle? It does, it's 0. How's that? The reason it has a 0 phase is because that's where I decided I was going to start my time. I just said, let me just assume for simplicity that this voltage, I'm going to start my time axis when the voltage is going through basically 0 degrees phase. That's going to be my origin. Once I've defined that, then I'm going to find my current or derive my current relative to that. But if in general this angle may not be 0 degrees, it might be 10 degrees, then your current, if you're just looking at the voltage and current on an inductor, the current will be behind that by 90 degrees, whatever that angle started out to be. If we assume that we're starting at 0 degrees for our voltage, did that answer your question? Then we're going to have this I sub M at an angle of minus 90 degrees, and now we can go into the time domain if we want to. We now have this V sub L of t is equal to V sub M cosine omega t. That omega was on the side of our paper. We were keeping track of that. And I sub L of t is I sub M cosine of omega t minus 90 degrees from the above or from that phasor representation. And we could say, well, if we want to deal with just sines and cosines without a phase shift, we could write that as sine of omega t for I sub L of t.
Sorry, why would you want to write it like that?
The question is, why would I want to write it like that? Because it makes my life easier in the subsequent analysis. But generally, we want to convert everything to cosines and then put them into phasor form. If we want to analyze these in phasors, I'm now just trying to illustrate what's going on with respect to the power in an inductor. And because of that, I'm going to say, let's look at what happens when I have the voltage and the current described by this for an inductor. where the voltage is a cosine, the current is a sine. The instantaneous power of that inductor is, again, the product of the voltage and current on that inductor. Using these functional forms that I've just introduced, we now have cosine omega t times sine omega t. Can I write that instead of a product of sine and cosine? Can I write that as just one sine or cosine, going back to your trig days? Yes, we could write it as squared, but I want to avoid squares, don't I, now? But do you remember the sine of 2 omega t? Or sine of 2 omega t? That's 2 cosine omega times sine omega. If we use that in the other direction, I could say, well, that's actually just 1/2 sine of 2 omega t. And again, I will refer you to a figure in the book, which I mysteriously happen to have, hopefully. And it's the one on the left. But let's look at that formula again before we go back to the picture. What is that telling us about the instantaneous power of that inductor? What's its frequency relative to the voltage or current frequencies? Twice. What would, if you calculated the average power of this inductor, what would it be? Over any period or a multiple, integer multiple number of periods, you integrate that sign, you're going to get 0, aren't you? The same amount of area above as below the axis. This guy has 0 average power, an inductor. That's kind of weird, but here's the picture. Hopefully this looks like, whoa. On the left is our inductive load. We have our voltage. The current is 90 degrees behind that. If we multiply the black and the blue point by point for each instant of time, we get the curve below, which is the instantaneous power on that inductor. And it's oscillating at twice the frequency. If we averaged that over a period, we would get 0 for the average power. So that inductor, a pure inductor that does not have any resistance associated with it, energizes the magnetic field, then it gives that back to the source. It energizes it, then gives that back. And that's what is happening with this inductor. When we apply a sinusoidal voltage which produces a sinusoidal current, the average power in an inductor is 0. That's one of the observations we can draw from that instantaneous power formula. And this power fluctuates at twice the frequency of V sub L and I sub L. Let me just write down a couple of sentences to try to help us understand what is going on. With respect to that P sub L of t, that instantaneous power, we can see that half the time energy is being absorbed, well, maybe I should say is being stored in the magnetic field of the inductor. That's half the time. The other half of the time, that inductor gives back that energy to the source. That's when it's negative. When it's positive, it's taking this energy in and storing it in the magnetic field of that inductor. When it goes negative, it starts giving it back to the source, that energy. So half the time, energy is being stored in the magnetic field of the inductor, while the other half of the time, the energy is being delivered back to the source from the inductor. Now the power company might not like that too much. If you're a big industrial facility and now you start drawing all this power in, and then the next half cycle of your period, what's the period in the United States coming out of one of these wall sockets? 60 hertz. 60 times a second, it's taking this power in and then it's throwing it back. Taking it in, throwing it back. Power company's probably not going to like that, so it's actually going to keep track of that. It doesn't like that necessarily. So because but then if it was charging you for average power, you would say, oh, I didn't use any average power. All I have is an inductor out here in the plant. And they're going, oh, your average power is 0. So 0 times something is 0. Question?
Is that assuming that it's perfectly efficient though?
So now the question was, is it perfectly efficient? Right now we're talking about a pure inductor. There's no losses in this inductor. We're assuming that this inductor is truly a pure inductor, and all of our plants, I'm going to call an industrial complex a plant. It's not a green leafy thing. It's an operating plant. That's going to have some resistance. But now we're talking about the pure inductor. And in the pure inductor, there is 0 average power. And because there is 0 average power, yet energy alternates, or alternately goes to and from the inductor. We're going to label this power. We term this power reactive power, and we're going to give it its own units and give it the units of VARs. That stands for volt amperes reactive. And the power company for these big, large facilities is going to keep track of not only your average power in watts, but it's going to keep track of your volt amperes reactive, your reactive power, your VARs. And it's going to start charging you for that. But before we talk about that, let's look at the last circuit element, which is this capacitor. again labeled the same way, passive sign convention, the current is going into the positive terminal of your capacitor. The impedance is complex, that's this 1 over j omega c, or in phasor form, that's 1 over omega c, that's the magnitude for a given frequency. If you fix the frequency, that magnitude will be fixed. J, if we write that as an angle when it's downstairs, is then this minus 90 degrees. And that's our complex impedance for a capacitor. Let's now do the same thing that we did before. Suppose that our capacitor voltage as a phasor, let's just arbitrarily say it's going to be at 0 degrees phase. Has a magnitude of V sub m, and it starts at 0 degrees, or that's the phase of the voltage. Then we can find the capacitor's current as the voltage across that capacitor divided by the impedance of that capacitor, and that's now going to be V sub m at 0 degrees over 1 over omega c at minus 90 degrees. Or that's omega c V sub m at an angle of 90 degrees. And if we don't want to keep track of all of that, those variables, we might just label that the maximum magnitude of your current, I sub m, at 90 degrees. That's the current phasor, I sub c. We can convert those phasor descriptions of voltage and current into their time domain representation. We know that they're operating at a frequency of omega, and we assigned the phase angle of our capacitor voltage to have 0 phase. That's now omega t for the argument of the cosine. For the current, that's I sub m, where I sub m is related to the voltage by what we just derived if you want to pull that more detailed information out. But we now have I sub m cosine omega t plus 90 degrees, or that's minus I sub m sine of omega t. Now we have those in a form that we would like to form the product of voltage current to give us the instantaneous power of that capacitor. That's now minus I sub m V sub m cosine omega t sine omega t. And we know what we're going to do with that. That's now going to be minus V sub m I sub m over 2 sine of 2 omega t. And we can go back and look at that figure also. And it's going to look similar to what the figure did for the instantaneous power of an inductor. If we go back and look at the right side of figure 522, again, it's going to have 0 average value if you were to integrate that. It's going to be at twice the frequency. Now your current is leading your voltage in that particular circuit element in your capacitor. Let's make some comments on what we've learned by just analyzing alternating current power in these 3 circuit elements: resistors, capacitors, and inductors. And in particular, let's just comment on this new thing that seems to be creeping or coming into the picture when we start looking at inductor and capacitor power. That now gives us reactive power. And you might say, why should we care? About reactive power if there's no average power in a pure. And what is average power? That's what you see on your power bill. That's the real power. That's the watts that you get charged for from the power company. That's your real power. That's the average power. But now if you had just an inductor sitting in your house, and that was it, you would just be charging that or storing energy in that magnetic field and throwing it back. Storing it, throwing it back. Storing it, throwing it back at 60 hertz. That may not seem like it's doing anything for you, and it's not really. But the power company's not going to like that. But there is no average power consumed by a pure energy storage element, which is either an L or a C. How many people have gone by a big substation, or it doesn't even have to be that big, and stood there? What do you observe? Do you hear anything? Zzz, something hum? You know something's going on, don't you? Something's happening. This throwing back and forth at a big industrial facility of this reactive power, there's still energy going back and forth. It's collecting, then giving it back. Collecting, giving it back. There's still current and voltage associated with that. If you now have current going both ways every half cycle, it's going to you, then you're throwing it back to me, throwing it back. That current's traveling on your wire. And what's the wire have? Resistance. The fact that you're pushing that power back and forth, you're actually having some resistive losses, even though maybe you're not giving or collecting any average power relative to those reactive loads. So there's still energy being pushed back and forth source to load, and the power system and by that I mean transmission lines, transformers. Is there a movie about transformers? Oh, that's a different kind of transformer. Sorry. Transformers are going to allow the power company to change that voltage, either step it up or step it down. And it is maybe to their advantage to step it up, to transmit it. Then there's not as much current to deliver the same amount of power, because now your voltage is really high, the current's not very large, and you don't maybe have as many I squared R losses, or your I squared R losses are reduced. But there's still energy being pushed back and forth, source to load, in the power system. Your transmission lines, your transformers, your fuses still need to, or still must be, sized or able to handle the current that's going back and forth, to handle the current with this reactive power. bottom line, that reactive power is going to make your I a little bit bigger than if you didn't have it there. You're going to have I squared R losses, and the power company is going to charge you, even though it's maybe not giving you any useful average power at your plant, they are going to charge you for what's going out the door from their company. And if they're having to push that across their transmission lines and it's experiencing I squared R losses, you can bet they are going to charge you for it, for a big industrial user. Questions on that? So now we're going to talk about real power and reactive power. Real power is, by the word, it's real. The reactive power, we're going to define that to be imaginary, and the combination of that real part and reactive or imaginary part is going to give us a vector that's going to be complex. And now we'll be dealing with complex power. Question?
Basically, if I understand this right, the power that we're charged for the households is caused by the resistance of all the utilities, or is like inductance and capacitance doesn't take up power. It's the average is zero. I'm kind of confused about that.
The question is, why or what am I getting charged for, I think, at home, and why are we even talking about these inductors and capacitors? I don't have any inductors on the couch, or that's not in my living room or in my office. I don't have any inductors sitting there getting energized and then giving it back. Well, if you have any kind of motors, they do have some inductive characteristics. But yours is not that significant, meaning a residential customer is going to only be charged for the real power that they consume. If you do have a lot of large motors, you're not going to probably get charged for it. This will make maybe a little bit more sense when we start talking about the complex power and you start seeing what the difference is between the real part and the imaginary part. A big industrial user might have a large number of motors. And that's going to, if you can play along, here's the real part that they are using to drive their machines, but then there's some inductive component because of the motors. Let's say this is the imaginary part. I'm getting ahead of myself. Here's the imaginary part and here's the real part. They are actually going to have to pay for using both parts. There's the complex power. Here's the real part. Here's the reactive part. The power company is going to keep track of that angle, which basically gives them a feel for the relative relationship between the real part and the reactive part or imaginary part. And this angle is going to give rise to a power factor, which we'll introduce in a minute. But they are going to get charged if that power factor is significantly away from 1. If you take the cosine of that angle, cosine of 0 is 1. If that angle is pretty small, meaning you have very little reactive power or imaginary power, that angle is still small, and the cosine of that angle is going to be close to 1. If your power factor of a big industrial plant gets below 0.8, there may be a surcharge that you have to pay. And they're going to say, oh, your power factor was 0.75. You have to now pay a tax, basically, on the use of the power because this vector is longer than this guy. We can't just charge you for the real part. You're actually asking for more than what we can maybe measure for real power, but they can measure all of this. They can measure the complex power, and now that's what I want to talk about for what we'll call general loads, which are made up of resistors, inductors, and capacitors all thrown into the mix. If you are an industrial user and you have a lot of these big motors that are looking like inductors, then you actually might put capacitor banks in your plant to try to negate the effect of that inductive reactance that you're consuming and bring that power factor, so it's called power factor correction. You may know that you are going to have a power factor of 0.7. Well, now you throw a bunch of capacitors on that, you put in your capacitor bank and bring that angle down, and now you have basically less complex, you have less reactive part, so your complex vector is closer in length basically to your real or average power vector length. Question?
So if the average power is 0, does that mean that the net energy input is also 0?
So the question, if you go back and look at those pictures for a pure inductor or a pure capacitor, you'll see that the average power is 0, but there is still power fluctuation, and it fluctuates at twice the frequency. And what the power company wants to do is try to minimize having that large reactive power on the system. And so if you have a big inductive load, you may want to try to balance that out with an equally large capacitive component, and then you can basically cancel each other out. And that's what we'll start looking at or talking about. But I'm probably talking before I give you enough to make any of this make sense. So let's get into the details. I saw another hand, but maybe I can move on. Let's look at this for general loads. Let's assume now that we have a voltage V of t being V of m cosine omega t. And let's assume that our current is I sub m cosine of omega t minus theta. And that theta now, because we don't know the mix of inductors and capacitors and resistors, that theta is not necessarily 90 degrees, plus or minus. It's just some angle. And that's the difference between our voltage and current. If we compute the instantaneous power for this set of voltage and current, then we have V sub m I sub m cosine omega t cosine omega t minus theta. This now is V sub m I sub m. Let's just keep the cosine omega t there, but let's now use the trig identity of cosine of the difference of two angles, which says that we now have cosine omega t times cosine of theta plus the sine of omega t sine of theta. That's just the trigonometric relationship between the cosine of A minus B, where A is omega t and theta is B. Question?
Do we have to have these trig identities memorized for the exam?
The question was, do I need to go back and study my trig? I thought you just did this for fun on evenings. I thought you went home and just looked at your trig books. You don't do that? Uh-oh, so I'm a little weird? I go home and just for enjoyment get out the trig book. I say, hey, where's my trig book? Huh? Pull it off the shelf and start reading. No, you probably won't have to, but you should be able to follow along and use the results that we will derive. This was for a particular circuit. We have a voltage and current. What do I know? And so theta is fixed. What do I know about these pieces? That's also constant, isn't it? If theta is fixed, the cosine of that fixed angle and the sine of that fixed angle will just give us a number. That's not varying with time. And we can rewrite this. We can say, okay, we now have this is equal to V sub m I sub m cosine of theta. That's just a fixed number. And And let me say that I now am going to combine the first pieces, and I have cosine squared omega t. I also have the other piece that was associated with the sine. I now have sine of theta, and I have that as the time-varying parts, sine omega t times cosine omega t. That's just algebra after I've used the trig identity. Let me now replace that cosine squared with what I have already used before, which is 1/2 plus 1/2 cosine 2 omega t. Or I now have, rewriting this, v sub m I sub m cosine theta. That's all, that product is just a number. Now let me rewrite that squared term as 1/2 plus 1/2 cosine 2 omega t. And the other piece I can say is v sub m I sub m sine of theta times 1/2 sine of 2 omega t. Do any of those pieces look familiar? If you looked back at what we talked about, this particular piece is actually the power associated with the resistive component, or the resistive part of the load. That's what our pure resistor looked like before. It was some amplitude times 1/2 plus 1/2 cosine 2 omega t. That's always non-negative, and it's oscillating at twice the frequency. This piece is not associated with the resistor, so this is the piece associated with the inductor and the capacitor, and we'll just lump those together and say this is now the power associated with reactive, which are these L's and C's, part of our load. This again is our instantaneous power of a general load. What happens if I compute the average of that? If I did this formula that somebody suggested would work, that's still going to work, isn't it? I take the power, integrate it over one period, and divide by that period. If I do that, though, there's basically three pieces in that P of t formula. The first piece is a constant piece. The second and third piece all are sinusoidal. Cosine theta and sine theta are just numbers. Those don't make it oscillate. The parts that make it oscillate are the 2 omega t pieces. If you look at this is actually going to simplify down to just the constant piece times the integral over which I'm integrating, which is one period, capital T, or the average power now for a general load is simply this V sub m I sub m over 2 times the cosine of theta. And hopefully you're seeing that complex power phasor diagram that I just put up before. Our average power, well, I'm getting ahead of myself. So let me wait. If we wanted to, and in this case we did have sinusoidal V's and I's, how are the magnitudes related to the RMS values? Or I could ask that another way. Suppose I split that 2 equally. I take the square root of it and I put one square root with V sub m and one square root with I sub m. I haven't changed that expression at all. But now does that V sub m over the square root of 2 look familiar as far as notationally? Did we call that something else? That's the RMS value of the voltage, isn't it? And I sub m over the square root of 2 is, for a sinusoid, the RMS current, all times cosine of theta. That's our average power, which is in watts. And what do we know about that theta? That theta is actually the difference between our voltage phase and our current phase. If you were thinking about a resistor and you said, okay, the average power of that resistor, or just in a DC circuit, you would say, oh, the power of that resistor is V times I. This sort of looks like that, except for that cosine of theta, and this cosine of theta is creeping in there because we now have inductors and capacitors present. That's now reducing our average power by a certain factor, depending on that angle theta, or the separation between our voltage phase and the current phase. The more our voltage and current are different in phase, or the amount that they're out of phase, that means that we have more reactive power than maybe we would like. And that cosine of theta is what the power company is going to be concerned with. If that starts getting much different from 1, they are going to start charging you more for the use of their power. And because of that, they call that out and they say cosine of theta, we're going to call that the power factor, and we may just say that's PF. So if you get a text with PF, you probably already knew that that meant power factor. Correct? Question?
Does that, well, the difference in the, whatever, does that apply to both of them, or just the?
So this is, we're now concentrating our attention. The question, I think, was, are we only worried about sinusoidal voltages and currents? I don't know if that was the question or not, but that's going to be my answer. Right now, we are going to concentrate on sinusoidal voltages and currents.
So we derived it for a cosine?
And we derived it for cosine. It could be the same if, well, what we're going to do is this, if you look back at what we ended up with, that cosine piece was actually associated with the part that's due to the resistive load. Here's the cosine piece right there.
What I was asking is, how did you do this for that little bit?
I can try.
All right, all right, how did you get from that, the average, to the second average? So were we doing cosines before, and now we're doing sinusoidal?
Oh, so now for sinusoidal V of t and I of t, I'm saying if V of t was a sine wave, it would have a magnitude V, capital V sub m, cosine of omega t. I of t would have capital I sub m, cosine omega t. If we have sinusoidal voltages and currents, and I said, show me the RMS value of that voltage. If you derive the root mean square expression for that voltage, if the voltage had an amplitude of V sub m, its RMS magnitude would be Vm over the square root of 2. Do you remember that from maybe a lecture or two ago? maybe you don't, but you'll go back and review that. All I'm doing is saying, oh, we can actually simplify this expression if we simply keep track of RMS magnitudes of voltages and currents. If we do, then the average power will just be voltage current times the power factor, where the voltage is the RMS voltage magnitude and the current is the RMS current magnitude. Then it's just like a DC resistor, V times I. It's not DC, we're in a sinusoidal system, and so if we do not have a purely resistive load, we're going to have some reactive part, and that will introduce this angle theta. Cosine of that angle then gives us the power factor, which when scaled or used to adjust V times I, RMS, gives us our average power. And we're going to call that cosine of theta the power factor. Meaning if we didn't have, or let me just keep going, here the product, VRMS, IRMS. I'm introducing quite a few new words. So this is the vocabulary part of 207. The product, VRMS, IRMS, is called the apparent power. That's what the power company looks like you're wanting to use. It's giving you a voltage and a current, but you're actually only able to use the real part of that, which is V times I, or VRMS, IRMS times the power factor. But this apparent power is given the units volt amperes, or VAs. Different from volt amperes reactive, which is the imaginary part. This apparent power is basically the magnitude of your complex power, V times I. Let's make an observation. The power factor, by definition, is the cosine of the angle theta, where theta is the difference between your voltage and current angles. But we could also find that cosine of theta if we took the average power, which is V RMS I RMS cosine of theta, and divided it by V RMS I RMS. Or depending on what you're given, you might be able to find this power factor many different ways. If somebody gives you the real power or the average power of a load, and then they say, oh, the apparent power is 10 volt amperes, and they said that the average power was 8 watts, you now know what your power factor is. It's the ratio of that 8 watts to the apparent power, which was 10 volt amperes. Your power factor now is 0.8. The power factor is the ratio of the real power to the apparent power. Let's just work through this again. So let's revisit all of this, and maybe if we revisit it enough, it'll start to feel a little bit more comfortable. Right now you might be getting a little nervous. We have average power and real power. You shouldn't be nervous about that. That's what keeps you cool on a hot day. That's turning your air conditioner. That's your watts that you're using. Now we're introducing the fact that, oh, maybe we want to keep track of this if we are in an industrial facility and your boss says, wait a minute, our power factor is 0.6, can you help me? Then you know, oh yeah, I've had 207, I know what we need to do. And you start saving your company millions of dollars, and you get a big bonus at the end of the year because of that. Okay? Now we're awake. Let's revisit this so that maybe we can save our boss some money, or your company. Here's V of t. In general, now I'm not going to set that phase at 0. I'm going to give it an arbitrary phase and call it theta sub v. Suppose that the I of t is now I sub m cosine omega t plus theta sub I. Question. This would be a gift on exam number 2. What if I said, give me the phasor form of the voltage? Give me capital V bar. Not V hat, V bar. What would that be? What would your answer be? A, B, C, D, or E, none of the above. Now what are you all going to answer on the next exam? You're never going to circle that none of the above. So now I'm going to have to put some of those on the next exam if we do it that way.
Wait, but I circled them on the lesson.
I'm sorry?
I circled many of them on the lesson.
I know, we all circled a lot of those on the last exam. That's the phasor form of V, magnitude at an angle. And they're both already cosine, so we can just write down their magnitudes and angles. If I said, actually give me the RMS value of the voltage in a phasor form, you could do that. Oh, you think that's funny. It is kind of funny, but what is V sub? So now you might say, but VRMS is what? That's Vm over the square root of 2. So if you give me those two pieces of information, there you'd get full credit, which sometimes in the way that I'm grading this, I might just put a 1 at the bottom of the paper. If I'm giving you all or nothing on an exam problem, if you see some 1s at the bottom corner of your page, that's my notation that you're getting full credit for that. You didn't get just 1. Hopefully you've now figured that out after looking at your exam and saying, how does this add up? I have 11 points. No, you probably had 10 points, or 20 points actually. All right, what's IRMS? Exactly the same structure with now the maximum amplitude of your current being divided by the square root of 2 to get or to obtain your RMS current number or value. Let's now use that in a circuit. Now I might draw something like the following picture. I might say, okay, here's a general RLC load. There's a phasor voltage, and there's the phasor current. We now want to relate all of these different powers that we've just defined today. Because apparently, oh, that was maybe a poor choice of words, because we have apparent power, we have real power, which is average power, we have reactive power. The units on apparent power are volt amperes, VA. Real power or average power, the units, watts. The units on reactive power,
Volt amp reactive.
VARs or volt amperes reactive. Okay? So let's now relate all of those. We have apparent power. We have real or average power. And we have reactive power. What did we say our average power was by definition?
V times I.
V times I with something else.
Cosine theta.
Times the power factor or cosine of theta, where theta is the difference between the voltage angle and the current angle. Our average power would then be V RMS, I RMS for that general picture, cosine of theta sub V minus theta sub I, where this is before what we were calling theta. But now knowing all that you know about Euler and different math, that's why you studied it, that could be viewed as just the real part of these complex phasors. VRMS, e to the j, theta sub v, and IRMS, e to the, what do I need to do to this phasor to allow me to come up with, when I just look at the real part, I end up with my angle being the difference between theta sub v and theta sub I. I now need to be minus j theta sub I. If I looked at this, I could call this complex number VRMS. If I tried to do the same thing here, IRMS should have a e to the j theta sub I. If I want to actually end up with minus j theta sub I, I need to take the complex conjugate of that current. Meaning now, if I want the average power, another way that I could think of it would just be to take the real part of my voltage in RMS times the conjugate of my current RMS phasor, and I have my real power or my average power. Meaning this I bar star is the complex conjugate of the current phasor. As an example, if I start with something like this, what's the conjugate? Another gift on exam number 2. None of the above? You just have to negate the angle, don't you, to find the conjugate. What if I gave it to you in rectangular form? Suppose I said, oh, here's I2, that's 4 plus J3. Is everybody familiar with that? Now what we want to do is, all I've done so far is found the real part of this complex voltage times the complex current. I want to actually just look at the complex power, which is all of that. And we'll have to pick up at that point, because I know you're not going to want to stay here another 2 hours to enjoy this material with me. So I'll see you on Thursday. Please make sure that I get your vote.